So Ludwig Schmidt is an assistant professor at Stanford University in the computer science department and at Stanford Data Science. His research interests evolve around the foundations of machine learning, often with a focus on data sets, multimodality, reliable generalization, and language models. In addition, he is also a member of the technical staff at Anthropic and Leon, an open source collective on developing language models. So Ludwig is maybe not necessarily a roboticist, but he's going to have a wealth of ideas and a huge amount of insight that I think will be very interesting for all of us roboticists to hear about as we start thinking about how we improve the reliability of robots. So Ludwig, with that said, please take it away.
Cool, thank you. Thank you for the very nice introduction. I'm super excited to be here today, at least virtually, because I think robotics is such a cool problem area. There's so much stuff that we still need to figure out, and I hope that maybe some of the ideas that I'm going to tell you about around reliable generalization and distribution shift are going to be a starting point for seeing if we can connect some of our ideas. Cool. Okay, so let's get started. I think Rohan just motivated this already really nicely, that as we take our machine learning progress from lab settings into the real world, this is often more challenging than we initially maybe hope or expect. And I think overall, it's such an exciting time in AI because we are bringing a lot of research developments from our research settings into the real world, like self-driving cars, again, as Rohan mentioned, and healthcare applications, robotics, various chat assistants obviously have made tremendous progress. And when we do that, it's, as you said, often it takes a longer time than you would hope initially. I remember 10 years ago, people were speculating how many million self-driving cars will there be on the roads by 2020, and it's definitely less than 1 million. If you live in San Francisco, you can take a Waymo, it's great, but overall this rollout has definitely taken longer than expected. And I think this is generally true for other areas like robotics as well. So one thing that interests me a lot on the research side is what can we do in order to make machine learning more reliable? And in order to study this problem in sort of like a scientifically very rigorous and principled, empirically backed way, I'm going to tell you a story around reliable generalization in the ImageNet universe. And of course, everyone knows ImageNet, probably the most impactful computer vision dataset ever. And I think one nice advantage that ImageNet has for studying distribution shift is that there have been so many models that people develop and so many out of distribution test sets that people developed. So it's a very rich experimental playground to do very detailed experiments and figure out what's going on. Cool. So what do I mean by this? A little bit more concretely. Of course, everyone knows ImageNet. As a community, we have made tons of progress over the past 10 to 15 years. But in many ways, and so at least 5 years ago when people were looking at this, and I think still now in various ways, the models are not as robust as you would like them to be. And in order to make this precise, sort of like very quantifiable and measurable, one very nice thing that the research community did around ImageNet about 5 years ago was build variants of ImageNet with the same class space, the same 1000 classes, but different distribution shifts represented in the test set. So more concretely, one project the collaborators and I at Berkeley did in 2018, 2019 was build a new test set called ImageNet v2 with a different crowdsourcing process. For around the same time, another group at MIT wrote a very nice paper called ObjectNet, where it was a similar idea. You take the ImageNet classes, but then you tell the crowd workers to introduce some distribution shift. For instance, often you would have chairs appear in the living room, and they instructed the crowd workers to take pictures of chairs upside down in the bathroom in order to introduce all these correlations that are normally not present in ImageNet. And then ImageNet Sketch, this is from a group at CMU, as the name suggests, this was simply the ImageNet classes, but now sketches instead of natural images. And ImageNet R is sort of like the ImageNet sketch idea supercharged. Instead of only sketches, a team at Berkeley built a variant of ImageNet where it's different renditions, hence the name R, of the ImageNet classes, basically kind of everything except a natural image of the actual object. Okay, and with all of these test sets, you can now study pretty precisely, are there any overarching trends? How can we make models more robust on out-of-distribution test sets? Okay. And in order to understand what's going on these out-of-distribution test sets in more detail, you're going to visualize the results in the following scatter plots. We'll go through this step by step, because these plots are key to understanding what's going on. Okay, so on the x-axis, by the way, can people see my mouse cursor?
Yep.
Yes, okay. And the x-axis, we plot the ImageNet top one accuracy, as you normally do. On the y-axis, we plot accuracy on an out-of-distribution test set, like ImageNet v2 here as an example. And then every marker here in the plot is one ImageNet model that we evaluated. We started here with all the standard ImageNet models from the SEML AlexNet over widely used architectures like VGG, ResNet, DenseNet, to an efficient net B7. This was state of the art when we did these experiments in 2020. And in order to orient ourselves, I've also put a dashed line in here. So this dashed line is the y equals x line, and y equals x means no change in classification accuracy from distribution shift. And what we see with all of these models is that there are two interesting phenomena. First, all of them see a drop on this distribution shift around 12 to 14 percentage points, and they all follow a very clean linear trend. So why this is still a good question that keeps me busy thinking about now and then. But for now, we can just take this as given. Basically, we are going to say, for a given in-distribution accuracy, this linear trend is going to tell us what the expected out-of-distribution accuracy for ImageNet models is going to be. And so basically, if someone gives me a new ImageNet model and they say, oh, this is super robust out of distribution, I can do the following. I can look at the ImageNet accuracy, 71%. Then I look at my baseline here. Okay, for 71% ImageNet accuracy, I would expect 58% ImageNet v2 out of distribution accuracy. And then if your model gets 58, it would be like, okay, this is exactly like what the baseline would suggest. There's nothing new here, really, unfortunately. But if you outperform 58 and maybe your model gets like 63% accuracy, would be like, okay, there's clearly something going on. This model clearly beats the baseline trend given by the ImageNet models. Okay, and we call this lift above the red baseline effective robustness. So this green star here, this is a hypothetical model that has non-trivial effective robustness because it's above the red line. And in order to convince ourselves that this entire effective robustness framework and this way of measuring robustness actually makes sense, we also did an experiment with 5 expert human labelers, where we randomly shuffled the ImageNet and ImageNet v2 test sets together and had the human experts label them, so they didn't know what they were labeling. And then what we found was that the humans are either on the y equals x line or very close to it. So this is a nice confirmation that in this framework here, if we want our ImageNet models to achieve human-like reliable generalization, then we want to increase the effective robustness and bring the models closer to the y equals x line. Cool. So this is the framework. And the obvious question at the time was, okay, in 2020, distribution shift, robustness was already a very active topic. Do any of the existing interventions help and increase the effective robustness of existing models? Cool. Like, just as a side note, if you have questions throughout the talk, feel free to interrupt me anytime. Like, if anything about the setup here isn't clear, let me know. Otherwise, also happy to do questions at the end. Okay, cool. Okay, so this is the measurement setup. Now the next thing we did was collect all the models with robustness enhancing interventions we could find, and we made the following plot. This is now, previously we had 80 models trained primarily for ImageNet. Now we have about 200 models on this plot. And the first impression when you look at this would be to say, Ludwig, this plot looks basically like the plot you just showed me. All of these models are quite close to the red line. And this is indeed the right takeaway here. Basically, all these robustness enhancing techniques that we tried did not help on the ImageNet v2 distribution shift. So this was adversarial robustness, various forms of data augmentation, people introduced special denoising layers into their networks, and so on. And all of these models are the brown points, and the brown points are all, again, quite close to the red line. The only models that stood out a little bit are some of the green markers here, the green points. And the green points are models trained on more data. For instance, on the top right here, we have a model JFT300M. This was trained by Google on 300 million images. So 300 times more data than the standard ImageNet models. And another model here, this was trained by Facebook. on 1 billion images from Instagram, so 1,000 times more data than training on ImageNet. And these models get about 1 to 2 percentage points lift above the red line, so 1 to 2 percentage points effective robustness. And here's another model. This was trained on the full ImageNet 21K class dataset that also sees a increase in effective robustness. And now you can look at this sort of like glass half full, glass half empty. The more data models clearly see a gain, but they need huge amount of data to see a relatively small gain. 1,000 times more training data, and then you close maybe 2 percentage points of the 12 percentage point gap. Okay. This was obviously so far everything just one distribution shift ImageNet v2. There's an obvious question, are these results representative for others? So let's quickly look at one more. In the paper, we have a ton more. And this is the ObjectNet distribution shift I mentioned earlier. Again, x-axis ImageNet, y-axis ObjectNet. And now the drop on this distribution shift is much larger. Like the red line is much further below the dashed line y equals x, about 40 percentage points. But apart from that, the plot looks pretty similar, and that there's still a quite clean correlation between in-distribution and out-of-distribution accuracy. And the only models that stand out above the red line are again the same models, the green points trained on more data. Okay, so there's taking a step back here, maybe from a robotics perspective now, a question, okay, Ludwig, you're doing all of these nice detailed experiments in the context of ImageNet. Do these phenomena also show up on other problems? And again, in the interest of time, we don't have sort of like the space right now to go through all of these results in more detail, but collaborators and I and also other researchers have done similar experiments in other domains. For instance, a group from Munich, they did similar out-of-distribution experiments for MRI reconstruction, medical imaging tasks. In a follow-up paper, we looked at pose estimation. A group at Google looked at object detection in the context of self-driving cars. And overall, this linear relationship is a good correlation between in-distribution and out-of-distribution accuracy is something that people also found in other domains. We also looked at this in the context of question answering, the squad data set, and then also tested more language models. Again, this is sort of like a brief overview here of sort of like 3 years of research, so we can't go and tell you about everything. But other researchers also independently found similar phenomena in a closely related experimental setup. So this is a very nice paper on domain generalization from a group at Facebook. This all came out in 2020. And in the abstract, they already say, we conduct extensive experiments using domain-bet and find that, when carefully implemented, empirical risk minimization shows state-of-the-art performance across all data sets. So they found basically similar results that, yes, people had come up with different domain generalization methods, but in the end, if you just do empirical risk minimization, you get as good or better out-of-distribution generalization in their setting also as the more specialized methods. Okay. Again, here's another paper that you can look at if you want to understand this accuracy on the line phenomenon in more detail. For now, I want to tell you about what comes next, or what came next. So this was sort of like the state at end of 2020. I thought I had this very crisp research problem. Clearly, out-of-distribution generalization is a challenge. There's this drop on the distribution shift, and what can we do now to fix this? And it turned out, without me knowing about this in parallel, a group of researchers at OpenAI was actually working on exactly the same problem. So in early 2021, the CLIP paper came out from OpenAI. I'm sure many of you know this paper. This has been sort of like really making a big step forward in multimodal learning. And one thing that was exciting for my collaborators and me was that in the blog post where they announced the CLIP model, the first set of results they highlighted were exactly these out-of-distribution improvements that we had studied and set up an evaluation framework for. So this is sort of like the screenshot from the blog post here. They compare their best model, a CLIP VATL, to an ImageNet trained ResNet 101. The two models are chosen so they get the same accuracy on ImageNet, 76.2%. So in our scatter plots, that means we are looking at the same x-axis value. So now we can look at the out-of-distribution numbers, and they'll directly tell us what is the effective robustness. And then what CLIP achieved was this very large gain in out-of-distribution robustness. So on ImageNet v2, 6 percentage point effective robustness, ImageNet R plus 50, ObjectNet plus 40, ImageNet Sketch plus 35. These are very, very big step forwards, right? So if you work on these data sets at the time, if you get a small single-digit improvement, you would write a paper about it. the CLIP paper achieved a large double-digit improvement. So as we said, this was super exciting. And Oleg and Jungwook, the first authors on this CLIP paper here, they actually followed exactly our evaluation recipe. They also made these out-of-distribution scatter plots, x-axis ImageNet, y-axis out-of-distribution accuracy, now averaged over 7 distribution shifts. And what you see again is that the CLIP model really stands out in terms of effective robustness. So the blue line here and the blue points are again the ImageNet trained baseline. The red markers, sorry, the green markers are the more data models that we discussed before that are better than the baseline given by ImageNet trained models. And then the orange line here is CLIP in zero-shot mode. And clearly CLIP in zero-shot mode is vastly more robust than any of the prior models. And sort of like when you look at this plot, there are two obvious questions that come out of this. The first one is, what makes CLIP so robust? And the second one is, what's going on with fine-tuning? This is an interesting side story in this plot here. So the red line is what you get if you take the orange line and you fine-tune these models on ImageNet. And what happens is, yes, if you fine-tune on ImageNet, your ImageNet accuracy improves. You move on the right on the x-axis, but the catch is the improvement on ImageNet does not at all translate to out-of-distribution improvements. In fact, the models actually get a bit worse out of distribution. And this was a bit of a bummer. And so another obvious research question here was, are there better fine-tuning methods that can get the best of both worlds? High in-distribution accuracy and high out-of-distribution accuracy. And the answer is yes. This was actually my first paper that I wrote with collaborators at UW, where I was an assistant professor for 2 years. And again, don't have time to delve into the details here, but if you're interested in robust fine-tuning, this could be worth to have a look at. What I want to tell you about more now is the first question. What makes CLIP so robust? And the title of this paper already gives it away. So the title is Data Determines Distributional Robustness in Contrastive Language Image Pre-training. Okay, so what did we do in this paper? Basically, this paper is a sequence of detailed ablation studies in order to understand where the CLIP robustness comes from. Because when CLIP came out, there was a range of natural hypotheses for what makes CLIP so robust. The first one is language supervision as an obvious candidate, right? So the whole point of CLIP was multimodal learning, that we now have flexible language supervision for image classification models, and standard ImageNet training doesn't do this. It just has 1,000 classes. This is the first hypothesis. The next one that's obvious is the training distribution. The ImageNet models are well trained on ImageNet, the training set. CLIP was trained on a different data set. We don't know exactly which one because it was proprietary to OpenAI, but it definitely was not ImageNet. The training set size could play a role. CLIP was trained on 400 million images, while the standard ImageNet training set is only 1.2 million images. Loss function is different, contrasted for CLIP versus standard supervised cross entropy for ImageNet trained models. Test time prompting is something you can do with CLIP models, but not with standard ImageNet models. And maybe the architecture plays a role. The best CLIP models are VITs, but most of the ImageNet models are convolutional neural networks. And again, what we did in the paper was decide experiments for each of them. And then the only thing that's left at the end, it actually comes out very crisply, is the training distribution. Again, don't have time to go through all the details in the paper. If you want to check them out, encourage you to have a look at the paper. I want to quickly summarize one of the key experiments to give you a sense of like, okay, what did we find in our experiments there? Again, scatter plot, x-axis ImageNet, y-axis average over distribution shifts. Blue line is the baseline given by training on ImageNet. And then the purple line are the CLIP models. And as we mentioned earlier, the CLIP models have a lot of effective robustness. And so we'll add 2 more models to this plot now. The first one is what happens when you train CLIP models on a much smaller data set, specifically the YFCC training set. From the OpenAI people, we know that the CLIP training set that they use is quite similar to YFCC. So they recommended to us that for smaller scale experiments, YFCC is representative for their training set. And indeed, you see that when you train a CLIP model on YFCC, it's lower accuracy, but it's still very close to the purple line. Okay. And then the next experiment we did was build an image caption data set for ImageNet, so you can train a CLIP model on the ImageNet images. So for context, ImageNet was built from Flickr, And all the images on Flickr have captions. It's just that in the ImageNet data set, they didn't keep the captions. So what we did was a lot of data detective work to link the ImageNet images back to Flickr and then build an ImageNet image caption data set using the original Flickr captions. And when you do this, then you get these green markers here. And the green markers are exactly on the blue line. So basically, if you do clip style training on ImageNet with real human provided captions, it's not giving you any effective robustness. So this was very nice evidence that the key part is not language supervision, but the key part is the more diverse training distribution. Okay, so this was the takeaway here. And then there's an obvious next question is, okay, if all the magic in Clip's amazing robustness is in the training data, like how can we make this even better with even better training data? And this is sort of like the second half of the talk now. Taking a step back now, I think an overarching question for all the people in this workshop probably is sort of like, what is the path to reliable generalization? And when I think about AI at a high level, I think about it as consisting of two parts, the algorithms and the data. And sort of like under the algorithms umbrella, we have all the things like optimization procedures, model architectures, loss functions, and so on. And people write thousands of papers about this in conferences like RSS, CVPR, NeurIPS, ICML, and so on. And we have made super amazing progress with this over the past 15 years. Like we have a very mature toolkit now to train highly performant language models, multimodal models, everything, right? So like the deep learning toolkit has become like very, very powerful. But at the same time, obviously the second half, the data part, is something we still study much less as a community. And I think as a result, we have sort of less guidance at the moment for how to build good training sets. I think to elaborate this a little bit more, I think one sort of key reason for why this happened historically in machine learning is that as a community, how we make progress and how we compare our results is often this benchmark paradigm, which I'm a big fan. I'm a big fan of standardized evaluations. This here is the MS COCO dataset, x-axis time, y-axis MAP. And as a community, we have made a lot of progress pushing up the MAP numbers, and we've learned a lot about how to build better models. What we have not learned at all is how to build good object detection training sets. All of these experiments here always hold the training set constant. So we have like no idea for how to build good training sets because no one has done controlled experiments on the training set aspect. And I think this is not just object detection. I think this is representatives for many areas of AI. And yeah, in the last few minutes, I want to tell you a little bit about research collaborators and I have started to do in order to understand better how we can build better training sets for AI. And in order to sort of like set this up, we need to start with the Lion dataset. I guess many of you have heard of Lion. It's a large image text dataset. And this also came out of the CLIP breakthrough from OpenAI. When we saw this and our colleagues in other institutions saw this, we were like, okay, we really want to train CLIP models, but we don't have the training data. And Lion 5B was a very nice large-scale collaborative effort in order to build a really large image text training set. So specifically, Lion 5B has about 5 billion image text pairs. And if you just look at the English part of Lion 5B, it's 2.3 billion image text pairs. And this was at the time 23 times larger than YFCC, which was the previous largest open image text dataset. And this was very exciting because this put us into the same order of magnitude as the large proprietary dataset at places like Google and OpenAI. Cool. Okay, and then like, how did we build this? At a high level, the Lion dataset creation process was the following. It was pretty ad hoc. We just wanted some large dataset and see how far we can get with that. So we, like many large AI datasets, we started with Common Crawl. We took 50 billion image text pairs from Common Crawl. Then we did some live web page filtering, downloaded the images together with the associated alt text. And then the important step in this pipeline was the content-based filtering. So what we did was take one of the OpenAI CLIP models that were now available, and for each image text pair, compute the cosine similarity between the image embedding and the text embedding. And then everything that's above a certain threshold, we decided to keep in the dataset, and that's it. As I said, like where this threshold came from, this was someone just playing around a little bit in the Jupyter notebook, all a little bit ad hoc, but this already got us pretty far. We could train some pretty good CLIP models with that. But then after we did the Lion dataset, we were like, okay, this is nice, but let's do everything again now from scratch, so we can do this in a experimentally more rigorous way, and we can make this a data-centric competition, hence the name Datacom. So one key component here was when people release data sets, they often only release the data, not the surrounding data processing infrastructure. And we wanted to now build a new data pipeline for creating Lion-like data sets, where the entire data pipeline is also available, so that people can reuse the data pipeline and build their own training sets. And then, as the name suggests, Datacom, dataset competition, we also wanted to set this up as a benchmark so that we can make progress as a community on this dataset creation challenge. And just to illustrate this a little bit, in traditional machine learning benchmarks, as I mentioned, the dataset is fixed and we improve the model. For Datacom, we flip this around. Now the model training code is fixed and we improve the dataset, or like the community, participants from the community improve the dataset. Cool. Okay, so a little bit more concretely, what do we provide? We provide a large candidate pool, again, from Common Crawl, of image text pairs at different scales. So different, if you're a researcher and you don't have that much compute, you can still participate at some of the smaller scales. We provide the standardized training code for CLIP models and an evaluation test bed of 40 downstream tasks. The idea being that we say a data set is good if with our standardized training code, the model that comes out does well on the 40 downstream datasets. And then there, as a participant, you submit either a new dataset with a given filtering method. So basically you come up with a new filtering method, use this to filter our candidate pool, train a model, and then this is an entry into the filtering track. Or if you have some other data source that you think is amazing and not covered by Common Crawl, you can also bring your own data and bring your own data track. Again, there's a lot more I'd love to tell you about, but we need to finish by 9:30 to keep things on track. So I'll just quickly highlight some results that we found here. So this is now measuring the quality of training CLIP models on 3 different training sets. All the same amount of compute. The original result from OpenAI got 75.6 on ImageNet. Then if you train a CLIP L14 on Lion, it's close, but it's about 3 percentage points worse. If you train a CLIP L14 on Datacom, our new data set that we put out as a baseline together with the competition, then you get 79.2. So this was the first public training set that was better than the OpenAI training set that they used for training the original CLIP models. And you can also think of these improvements as a compute improvement. We could push things to 79.2% with the Lion training set before, but it required training a larger model and a lot more compute. Okay, so now let's wrap up. There's a lot more stuff, again, I would love to tell you about, but we don't quite have time for it. One thing that I think is nice to highlight here, that since we put out the Datacom paper, the community has made many nice contributions on better data curation techniques. So this is the leaderboard as of 2 weeks ago. So like at the bottom here, we have Lion and our first entry with Datacom 1B. And since then, various researchers have made nice progress pushing up these numbers. Cool, but for now, again, we'll skip over a little bit more here. Okay, we did also all of this for language models. Okay, so this entire Datacom framework, you can apply it to other domains. Can you build better training sets for language models, for instance? Yes, we did this last year. This year we did this for reasoning models. This was the Open Thoughts project. Again, lots more cool stuff going on in the dataset world right now, but we do have to wrap up, so let me conclude. So I think the main takeaway of this 5 years of research here has been that training data is very, very important for reliable generalization. Like the CLIP model made this very clear because we had this very broad set of evaluations for the ImageNet world that stood out from the beginning. And then there's the obvious question, okay, if CLIP is robust, what's the cause for the robustness? As we said, training data, it's not only scale, but some measure of diversity that I can't really quantify beyond it does really well on many data sets. And to be a little bit more precise, so the role of training data diversity versus language supervision. As we said earlier, the language supervision itself is not causal, directly causal for CLIP being so robust. But one thing that's really nice about language supervision is that it's very flexible. And basically, what language supervision allowed the OpenAI team to do is build a training set with many, many images that don't necessarily need to fit into the ImageNet class hierarchy. So before we had flexible language supervision, if you wanted to build an ImageNet training set, every image had to fit into one of the 1,000 ImageNet classes, and that implicitly was a strong selection bias. You only used images that were clean ImageNet-like images, and then with CLIP, they could throw everything into their training set as long as it had a valid text annotation, and that allowed them to build a much more diverse training set. Cool. Okay. I think there are many open questions here. I think the big one is, how do we build better training sets so we get more broadly reliable models? And I think there's a question, what do you do? Like, do some of these phenomena around distribution shift that we've seen in a recognition setting here, like ImageNet, also apply to reasoning tasks that LLMs do? Cool. If you want to learn more about this, you can go to datacomp.ai, and I am happy to take 1 or 2 short questions now. Thank you.
As our next speaker starts getting set up, maybe we can take 1 or 2 questions. You should be able to just speak out and we should be able to hear you, but if not, I can relay any. Yes?
Hi, thanks Ludwig for the
Maybe you
talk.
need to speak.
Oh yeah, so you mentioned that fine-tuning can also make the model less robust. So I'm wondering, like, what do you think is the fundamental challenge for fine-tuning? And then how can we enable like fine-tuned models to be specialized in one target domain, but also remain generalist?
Yeah, it's a good question. So I think what basically happened with fine-tuning there is that if you fine-tune only on ImageNet, you can, even though you've pre-trained a model on this large data set with a lot of compute, it's relatively easy with fine-tuning to erase a lot of this pre-training knowledge. So when you fine-tune, you also need to keep this pre-training knowledge. And one surprisingly simple way to do this for these CLIP-style models was you simply average the weights. You take your zero-shot model, you fine-tune it, and then you average the weights together. And that model already gives you both good in-distribution and out-of-distribution robustness. I think in other settings, weight averaging maybe doesn't work as well, but I think the overarching ideas don't only fine-tune, also keep some of your pre-training loss or some of your pre-training data around so that the model doesn't forget that part of the distribution.
Maybe 1 more question. All right, then with that, let's thank Ludwig once again. And
Cool, thank you. See you later. Bye.